Welcome to the technical seminar in thermal analysis. My name is Lani Celiz and I will be your presenter. Today's topic focuses mainly on food applications using simultaneous thermal analysis or STA and differential scanning calorimetry or DSC methods. The International Confederation for Thermal Analysis and Calorimetry defines thermal analysis as a group of techniques in which a property of the sample is monitored against time or temperature while the temperature of the sample in a specified atmosphere is programmed. The physical properties evaluated by thermal analysis and their appropriate techniques are listed on this table. For changes in mass and the temperature difference between a sample and a reference material, the simultaneous thermal analysis or STA composed of thermogravimetry and differential thermal analysis method is used. For quantifying the energy in a reaction, the differential scanning calorimetry or DSC method is applied. The common reactions in food that can be measured by thermal analysis are listed on this table. For reactions such as melting, crystallization, glass transition, phase transition, gelatinization, oxidation can be evaluated by both STA and DSC, while reactions such as dehydration, combustion, decomposition, and water vapor absorption are recommended to be analyzed by STA. From this slide onwards, we will be introducing applications using differential scanning calorimetry or DSC. DSC or differential scanning calorimetry is defined as a technique in which the energy of a sample under a programmed temperature change is monitored as a function of temperature or time. DSC measurements provide qualitative and quantitative information on the physical and chemical changes that produces the endothermic reaction such as melting or phase transition or exothermic reactions such as crystallization, oxidation, hardening, phase transition, or baseline shifts such as in glass transition or in glass transition with enthalpy relaxation. Basically, there are two types of DSC systems, the power compensation type and the heat flux type DSC. The Rigaku DSC is a heat flux type DSC. Here is an example of a DSC data plotted against temperature. Looking at the DSC curve, our first reaction is a baseline shift near 77 degrees centigrade due to glass transition, indicating the existence of amorphous regions within the material. It is followed then by a positive peak or an exothermic reaction at 151 degrees centigrade due to crystallization and a negative peak or endothermic reaction at more than 200 degrees centigrade due to melting. By analyzing the data, we can obtain information such as onset temperature, peak top temperature, amount of energy in a reaction, or enthalpy. In a DSC data, it is important to indicate the direction of an endothermic or exothermic reaction. The DSC applications that we will be discussing are thermal behavior of pure cocoa as affected by cooling and storage, crystallization and melting behaviors of fats and oils, thermal behavior of new and aged olive oil and canola oil, and gelatinization of starch. Our first application is on the melting behavior of pure cocoa as affected by cooling and storage. Cocoa is a final raw material fermented from cacao beans, and it is used as a base material in chocolate products. Cocoa butter is a pure vegetable oil derived from the beans of cacao plant, composed of unsaturated fats with more than 95% fatty acids containing high levels of triacyl glycerols, palmitic acid, oleic acid, and stearic acid. Over the years, the differential scanning calorimetry plays an important role not only in characterizing the melting behavior of cocoa butter, but also in the quality control of a product. In this application, we demonstrate the significance of DSC on the melting behavior of cocoa as affected by cooling rate and storage. This slide shows us the temperature measurement conditions of the pure cocoa, which involves repeated cycles of heating and cooling. All heating processes were carried out at 5 degrees centigrade per minute with varying cooling rates of 5 degrees centigrade per minute, 2 degrees centigrade per minute, and 1 degree centigrade per minute. After which, the sample was stored for 12 days and was heated again at 5 degrees centigrade per minute. In the first heating, we can observe that the melting behavior is sharper, revealing a different melting peak compared to the second, third, and fourth heating. This is due to the effect of thermal hysteresis of the sample. By performing melting on the sample, we are able to cancel the thermal hysteresis of the material. However, as we heat or cool, we are imposing a new set of thermal hysteresis on the material. Furthermore, we can also observe the difference in crystallization peaks, which indicates that the cooling rate has affected the formation of crystals in a material. With the obtained data, we created a multiplot on the measurement results. The blue curve is the melting reaction of the original sample. The black curve, green curve, and red curve are the different melting reactions with varying cooling rates of 5 degrees centigrade per minute, 2 degrees centigrade per minute, and 1 degree centigrade per minute, respectively. The pink curve is the melting peak when the sample was stored for 12 days after cooling at 1 degree centigrade per minute. Notice that the melting behavior is observed at lower temperatures on the second, third, and fourth heating with peak top temperatures between 20 degrees to 21 degrees centigrade when the sample was cooled at different cooling rates. In addition, storing the sample for 12 days shifted the melting reaction near the original sample with a peak top temperature of 33 degrees centigrade, which is 2 degrees centigrade lower compared to the peak top temperature of the original melting reaction. The overall aim for most chocolate manufacturers is to produce a more stable chocolate, which will not convert to another crystal form during storage, and to be able to produce a characteristic product. This can be investigated thoroughly using DSC. The numerical values of the analyzed data are shown in this table. Notice the difference in onset temperature of the melting reaction, peak top temperature, and enthalpy, and the difference in enthalpy ratio compared to the original sample. The melting energy or enthalpy of the sample with different cooling rates are approximately 60% compared to the fresh or original sample's melting energy. On the other hand, storing the sample for 12 days has increased the melting enthalpy ratio to 96%. DSC Vesta is also equipped with a visual monitoring capability as an option that allows you to confirm the visual changes in the material as it goes through a reaction, obtaining new information and insights. Through this option, you can create a movie on the captured images with the analyzed data. With a sample observation attachment, you can also use together with an auto sample changer and also a cooling option such as refrigerated cooling unit. Here is a movie captured with sample observation DSC on a commercial chocolate. However, with the increasing and unpredictable price of the cocoa butter, manufacturers and researchers have investigated the use of alternative fats for cocoa butter such as coconut oil. Here we compare the melting behavior of cocoa butter and coconut oil. Although they both differ in the melting behavior, the coconut oil is believed to produce a physical effect similar to the cocoa butter. In our next application, we compare the crystallization and melting behavior of different oils produced from plants and animals by DSC. Fats and oils are derived from plants and animals, which are both composed of triglycerides. Although vegetable oils such as canola oil or olive oil are also composed of saturated fatty acids, it mainly consists of triacylglycerides composed of unsaturated fatty acids, and their composition depends on the botanical origin of the oil. While animal fats are mostly composed of saturated fatty acids than unsaturated fatty acids. In this application, using the DSC Vesta equipped with refrigerated cooling unit, we measured the crystallization and melting behavior of oils and fats, measuring from minus 70 degrees centigrade up to 70 degrees centigrade. We measured coconut oil, canola oil, olive oil, red palm oil, lard or fat, and beef fat or beef tallow. The measurement conditions on analyzing the crystallization and melting reactions of fats and oils by DSC are written on this slide. We used an aluminum seal pan where we prepared a 6 mg sample amount, heating the sample at 2 degrees centigrade per minute and cooling at 5 degrees centigrade per minute, continuously measuring twice. Notice the difference in melting behavior of the first and second heating result. This is due to the effect of thermal hysteresis of the sample. Therefore, heating once cancels the effect of thermal hysteresis on the material. Thus, when comparing samples, we use the second cooling result to monitor on the crystallization phenomena and the second heating result for the melting behavior of fats and oils. The different melting and crystallization behavior of fats and oils used in this experiment are shown in this slide. Our results reveal that fats and oils differ in melting behaviors as well as crystallization reactions, indicating their differences in glyceride contents, fatty acid contents, as well as other physical component that serves as a characteristic or fingerprint of the oil. We have also compared the thermal behavior of a new and a 9-year-old olive oil stored in dark bottle at room temperature. The green curve is a new oil which is characterized by an exothermic peak near minus 22 degrees centigrade due to the rearrangement of metastable crystals to a more stable form and continuously followed by melting of two different crystalline structures. Comparing this with a 9-year-old olive oil, we can see the difference in onset temperatures, peak forms, as well as melting enthalpy. When overlapping curves in the measurement result is obtained, using the partial area function in the EVO2 analysis software, we can analyze partial peaks in an overlapping reaction. Our next application is on starch gelatinization. Food cooking and food processing conditions depend strongly upon the gelatinization property of starches. Starch gelatinization is the disruption of molecular order within the starch granule. It results in a granular swelling, crystallite melting, loss of birefringence, viscosity development, and solubilization. A variety of analytical techniques have been applied to study starch gelatinization. DSC is the easiest way of evaluating the temperature and enthalpy of the gelatinization reaction by observing the endothermic reaction. In general, starch composition influences its gelatinization behavior, and it differs depending on the botanical origin of the starch granule. The gelatinization onset temperature and the enthalpy increase as the length of the amylopectin chain increases, which is related to the crystallinity of the starch granule. On the other hand, the gelatinization end temperature increases as the amount of amylose increases, which is related to the amorphous content of the starch granule. The DSC gelatinization data provides essential parameters which are related to the end-use properties of the starches. We compare the gelatinization behavior of different starches, namely sweet potato, rice, corn, tapioca, potato, and wheat. The gelatinization temperature differs depending on the botanical origin of the starch, and it serves as a fingerprint in identifying starches. The onset temperature of the gelatinization process and the enthalpy increases with increasing crystallinity, and the onset temperature increases with increasing amorphous content of the starch granule. Among all starch shown in this data, the potato starch reveals a higher crystallinity, and the wheat starch shows the lowest. With the DSC Vesta, we can perform measurements equipped with sample observation option, UV irradiation attachment, or with other cooling options that allows us to measure at a wider range of temperature that can correspond to different kinds of materials. From this slide onwards, we will be talking about simultaneous thermal analysis. Simultaneous thermal analysis, or STA, is a simultaneous measurement technique composed of thermogravimetry, or TG, and differential thermal analysis, or DTA. TG, or thermogravimetry, is defined as a technique in which the mass of the sample is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. Moreover, the differential thermal analysis, or DTA, is a technique in which the difference in temperature between the sample and a reference material is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed. Rigaku's STA system is a horizontal differential type. The typical profiles obtained by STA are shown in this slide. The TG is indicated by the green curve, which may result as no change in mass, or an increase in mass, or a mass loss reaction. On the other hand, the DTA curve is shown by the blue curve, which can be described as a negative peak revealing an endothermic reaction, or a positive peak indicating exothermic reaction. By combining both TG and DTA, or DSC, we can estimate the kind of reactions in a material on a given measurement condition. This is an example of an STA data, or TG-DTA data, where the TG curve provides information on mass changes such as mass loss or mass increase, quantified in terms of milligrams or percentage. On the other hand, the DTA curve provides information on a reaction that can be described as endothermic reaction or exothermic reaction expressed in microvolt. However, it cannot quantify the amount of energy directly. However, on a TG-DSC curve, through temperature and energy calibration, we can quantify the amount of energy in an endothermic reaction or an exothermic reaction, which is expressed in joules per gram. The applications for STA are melting behavior of sugar by sample observation STA, thermal behavior of artificial sweetener, Trehalose dihydrate, and oxidation phenomena in cooking oils by sample observation STA. This is an STA measurement result of sugar measured from room temperature up to 650 degrees centigrade under air atmosphere. At 200 degrees centigrade, we can observe an endothermic reaction due to melting of sugar. And as the temperature increases, we can see two endothermic peaks at 235 degrees centigrade and at 281 degrees centigrade, which corresponds to two mass losses. In these reactions, the carbohydrate in sugar goes through dehydration reaction and caramelization phenomena. Then from 350 degrees centigrade, we can see an exothermic reaction corresponding to another mass loss due to the combustion of carbon in sugar. Before we move on to our next application, I would like to introduce to you our sample observation attachment for STA. Existing customers with Thermoplast Evo 2 STA 8122 equipped with a standard furnace can later purchase the electric furnace with a built-in sample observation unit as an add-on option. With these attachments, the user can easily replace the standard furnace to a sample observation unit. This slide shows us the movie of the thermal behavior of the granular sugar by sample observation STA. The first reaction that we are going to observe is at 187 degrees centigrade, where there is melting of sugar. Here you can see the change in shape of the material. And the next reaction is a dehydration, and after that caramelization, after which there is the combustion of carbohydrate in sugar. And as the temperature increases, we can see mass loss. Then at around 600 degrees centigrade, we can see that there is a 100% mass loss on the sugar. Therefore, by using the sample observation attachment, we are able to confirm the visual changes such as change in color, shape, size, as different reactions occur in the material. Sucrose is the most common sugar known as the table sugar. It is a glucose derived from plants, mainly composed of carbohydrates. On the other hand, artificial sweeteners are synthetic sugars used as substitutes for health purposes, mostly found in carbonated drinks and recently available for household consumption. Here I have shown a few examples of artificial sweeteners such as aspartame, saccharin, and sucralose. This is an STA result of artificial sweetener measured in both inert atmosphere and air atmosphere. Both conditions revealed an endothermic peak near 120 degrees centigrade due to melting, followed by a single mass loss with an endothermic peak at 270 degrees centigrade due to evaporation, and a 100% mass loss can be observed at 300 degrees centigrade. Here we compare the thermal behavior of table sugar and artificial sweetener measured in air atmosphere. Unlike the sugar, since artificial sweeteners do not contain carbohydrates, we cannot observe the exothermic reactions due to caramelization and combustion that we have observed in granular table sugar. The STA method could be an essential tool in detecting contamination with counterfeit artificial sweeteners. Trehalose dihydrate plays an important role not only as an excipient and a stabilizer in the pharmaceutical industry, but also it is an essential component in the food industry responsible for maintaining fresh flavor and texture in food. In this application, the sample observation STA method is used for the measurement of trehalose dihydrate. By using the sample observation unit, the user can clearly confirm the actual visual changes in trehalose dihydrate as it goes through dehydration, change in color as it goes through amorphization, crystallization, and loss of shape during melting, and change in color as it goes through combustion. Trehalose dihydrate is a widely known material in food and pharmaceutical industry. This material can exist in crystalline form, anhydrate form, and amorphous form depending on its particle size. In this application, the use of mechanical method by mortar and pestle was applied to reduce the particle size to fine powder. Here, the STA method is used to confirm the thermophysical changes of the powder and original sample of trehalose dihydrate. Results reveal that heating the original sample exhibited an endothermic peak at 100 degrees centigrade accompanied with mass loss due to dehydration. At this point, the sample changed to anhydrous trehalose. Then at 208 degrees centigrade, we can observe an endothermic reaction due to melting. On the other hand, the powdered sample shown in blue curve clearly revealed two overlapping endothermic peaks due to dehydration at 86 degrees centigrade and at 101 degrees centigrade, and a mass loss due to dehydration. After the dehydration reaction, a change in baseline can be observed at 138 degrees centigrade due to amorphization. Finally, an exothermic peak due to crystallization can be found at 195 degrees centigrade, immediately followed by an endothermic peak due to melting at 212 degrees centigrade. This clearly confirms that the fine particles formed an amorphous phase upon dehydration of trehalose dihydrate. Evaluating the oxidation of cooking oils through analytical techniques are mostly carried out through chemical methods based on molecular markers of lipid oxidation, which is tedious, time-consuming, and expensive. On the other hand, the use of thermal analysis, such as STA, does not require a complicated sample preparation procedure and generates data on a shorter measurement time, which is less expensive. In our next application, we demonstrate the advantage of STA equipped with sample observation attachment in the oxidation evaluation of cooking oil, such as red palm oil. Over the years, the analytical method in confirming the actual change in color in relation to auto-oxidation in oils required a series of analytical procedures involving complicated extraction methods. But with the advantage of sample observation attachment in STA, these changes in color due to oxidation can be easily confirmed. Here is a movie on the oxidative decomposition and combustion phenomena of cooking oil by STA using red palm oil. The first phenomena is melting, and as the temperature increases, we can see the first mass loss, which is caused by the auto-oxidation, causing discoloration, most likely due to color reversion phenomena. We can clearly elucidate the change in color in relation to different stage in oxidation reaction, carbonation, and finally, combustion of the red palm oil. Then at around 600 degrees centigrade, we can observe a 100% mass loss. This slide shows us the difference in oxidative decomposition and combustion behavior in other fats and oils such as coconut oil, canola oil, olive oil, lard or pork fat, and beef fat or beef tallow. Results show that beef fat revealed an initial mass loss near 180 degrees centigrade due to oxidative decomposition, followed by coconut oil with a mass loss near 280 degrees centigrade, while other samples such as canola oil and olive oil and lard revealed mass losses starting near 300 degrees centigrade. All samples exhibited exothermic reactions during oxidation reaction and combustion reactions. The STA system can be utilized as a standalone system that can be connected with a wide range of options such as sample observation option, humidity generator system, and even systems for evolved gas analysis technique such as STA-FTIR, STA-GCMS, or STA-MS that suits your need. These are our available products in thermal analysis. We have STA-8122, where you can measure from room temperature up to 1500 degrees centigrade. DSC Vesta, where you can measure from minus 170 degrees centigrade depending on the cooling option. And Evolved Gas Analysis System with the commercial name Thermomass Photo, where you can measure up to 1000 degrees centigrade equipped with a skimmer type interface and with electron ionization and photoionization techniques available as a standard. Other products such as TMA 8311 as well as other hyphenated techniques such as XRD-TSC and evolved gas analysis systems are also available. All these systems have a wide range of options that will provide solutions to your needs. We provide not only lectures and hands-on training sessions, but also live online demonstration on your samples for free. If you have some inquiries, you can send us an email on the email address provided on this slide. Thank you for your interest and for attending this webinar. We hope to see you again in our future sessions.